Good afternoon. This is our last video lesson for the semester and our last video lesson for the atmosphere and weather unit. There is a video lesson already up on Canvas from before, some other semester, and there may be a little bit of overlap, but this is what we did in class for our last week for people that were in quarantine or otherwise couldn't make it. All right, so this never takes the place of actually coming to class. There's going to be some things that you're not going to get because we also looked at slides, but the narrated version of that PowerPoint is on Canvas. All right, so let's begin with the dates of the solstices and equinoxes, okay? So you're going to need to know these. You're going to need to know on what date they happen. You're going to need to know where the sun's rays are vertical and on that date and so forth. So, and of course we will focus on the northern hemisphere because that's where we live. All right, so summer solstice is the first day of summer. Everybody knows that's the longest day of the year, right? Most hours of daylight. So the sun's rays are vertical where? They are vertical at the Tropic of Cancer, which is 23.5 degrees north latitude. And on what day is that going to happen? It's going to happen on June 20th or 21st. Okay, how about the winter solstice? I hope we have enough charge on our battery. I think we do. All right, so on the winter solstice, that's the first day of winter. Everybody knows that's the shortest day of the year, least hours of daylight. Sun's rays are vertical where? 23.5 degrees south latitude, also known as the Tropic of Capricorn. And on what days is that going to happen? 21st or 22nd? So on the narrated PowerPoint, again, I'm expecting everybody to watch those and take notes. And there are a couple of really good drawings dealing with the seasons and why Earth has seasons. So you're going to need to go in and watch that as well. All right, how about the fall equinox, first day of fall? Everybody on the planet will have 12 hours of daylight, 12 hours of night. Where are the sun's rays vertical? At the equator, 0 degrees. And this is going to happen on either September 22nd or 23rd. Okay, how about the spring equinox? First day of spring. Yet again, everybody on the planet will have 12 hours of daylight, 12 hours of night. Where are the sun's rays vertical on that day? Again at the equator. And that's going to happen on March 20th to 21st. Okay, next we're going over here to how the troposphere is heated. All right, so this is a 3-step process, okay? So the first step is that first bullet there. About half, or 50%, of the incoming short wavelength radiation from the sun is absorbed by land and sea surfaces. Okay, so we only make use of half. So what happens to the other half? Well, it's lost, either through reflection, scattering, or absorption. It doesn't matter. We don't need it. We do just fine with the 50% that we get. So the Earth soaks up that energy, the 50%, and then it's going to re-radiate it or spit it back out. Okay, so it's going to re-radiate this energy at a longer wavelength in the infrared zone, which is heat that you can feel but not see. Okay, and why is there a wavelength change? Because the Earth is not as hot as the sun. Good thing. If it was, we couldn't live here. Okay, step 3 involves the greenhouse gases. So the greenhouse gases in our atmosphere then trap this energy and heat the air around us, heat the troposphere, the lower layer of the atmosphere. So we do need greenhouse gases, okay? But we also need to keep a close check on them. We don't want their percentages to increase, okay? That is happening already. Don't forget that carbon dioxide, when I first started teaching here 12.5 years ago, the percentage was 0.037%. It's now closer to 0.04%. It's gone up in a very short amount of time. By the way, the greenhouse gases are listed in the narrated PowerPoint. We've got water, carbon dioxide, methane, nitrous oxide, and then the hydrofluorocarbons, which we use now for propellants instead of the chlorofluorocarbons. Remember, we cut out the use of CFCs because they were putting a hole in the ozone layer. Anyway, by the way, just so you know, why do we worry about methane levels? Levels of methane are a smaller percentage even than carbon dioxide. Here is why. Methane is anywhere from 6 to 24 times more powerful a greenhouse gas than carbon dioxide. So we have a phrase for this type of heating, or how the troposphere is heated, and that's the last bullet here. We call it terrestrial re-radiation. Terrestrial simply referring to the Earth. By the way, I'm going to walk to the other side of the room so that the light doesn't cut out on me while I'm filming, because that kept happening while I was putting this on the board. Okay, now we can go back and film. Okay, where are we going next? Next we are going here to the, well, we're going to go to the green at the bottom, then we'll go to the purple. Okay, so humidity. Humidity is simply referring to the amount of water vapor in the air. And if I were to ask you guys, as I did for people that were in class, which air mass could hold more water vapor, a warm air mass or a cold air mass? And of course that answer is a warm air mass. We know that from living in the South. Yeah, definitely. Our high humidity days in the summer, in the warm months, feel a lot worse than they do in the winter, in the colder months. But we're going to express humidity in the form of relative humidity. Okay, so that is the amount of water vapor in an air mass compared to how much it could hold at that temperature. It's always expressed as a percentage, and if the relative humidity is 100%, that means that the air is saturated. So when this happens at the surface, which it occasionally does, then we should expect to see fog and or dew. But now we're going to move up here to the purple, okay, because we're going to see that the relative humidity we are most concerned with here is what happens at a higher altitude in the troposphere, as in cloud formation. Okay, so that brings us to our next topic, the dew point temperature. This is the temperature to which a parcel of air needs to be cooled to reach saturation, or 100% relative humidity. Okay, so lifting of air and cooling of that air as it rises, lifting and cooling is the dominant control on cloud formation. Now, lifting mechanisms are discussed on the narrated PowerPoint. In class today, we did look at some drawings. One of the slides has a set of 4 drawings, the 4 basic types of lifting mechanisms. We briefly discussed orographic lifting, and we discussed frontal wedging or frontal lifting a little bit as well. Okay, so here's the thing. Imagine that you are climbing a tall mountain, Mount Rainier volcano in the Pacific Northwest, or maybe Mount Everest in the Himalayas. Everybody knows as you go higher and higher up in altitude, it gets colder, okay? So as air, warm, moist air, is rising in the troposphere, it's going to cool more and more as it rises up. At some point, it'll cool enough that it'll either hit or go below the dew point temperature. That's when you will hit saturation, and you will have condensation, and you will start to form clouds. Okay, our next topic, mid-latitude cyclones. Okay, so that drawing there might look a little funny. It might look like a jellyfish or something. There's a pretty good drawing of these in the narrated PowerPoint. Okay, so it begins with the red L there, okay? Because this is a cyclone, just like any other cyclone, which means what? It's a low pressure center. So we show them on the weather map with a red L, okay? L for low, red for warm air. Okay, I did not write that down, but I'm speaking it, so please add that to your notes. Our cyclones are associated with warm, rising air. All right, now these things are indeed the primary weather producers in the United States, and there's a warm front on the leading edge and a cold front on the trailing edge. So you see the warm front there, it's a red line with semicircles. You see the cold front, it's a blue line with triangles. In green is an outline of where we expect to see clouds, okay? So we expect to see clouds around that low center, which is that roundish thing that you have at the top with the big red L in it. Why? Because it's warm air. Everybody knows how a hot air balloon works, right? Why does a hot air balloon rise? Because you're heating that air. Okay, and they have to, there's a stove on board that balloon because they have to continue to heat the air or they're not going to stay up in the air, okay? So the air is rising there at the center where the L is. And as that air is rising, it's cooling and condensing, you get cloud cover. Well, you also are going to get clouds along the warm front and the cold front. And that is because where you have fronts or boundaries between different air masses, in other words, you have the clashing of warm and cold air masses here in the United States all the time, that's going to be a type of lifting mechanism. That lifting mechanism is known as frontal wedging or frontal lifting. We discuss it in the narrated PowerPoint. Okay, now we are going to focus in particular on the warm fronts and the cold fronts. Okay, so your warm front, again, which is on the leading edge, meaning the forward edge of our mid-latitude cyclone. What does that mean, a warm front? A front, by the way, is just simply a boundary between two different air masses that are different temperatures and therefore different densities. Okay, so a warm front, warmer air is moving in. We're going to show it on the weather map as a red line with semicircles. What kind of clouds do we expect to get? Eventually, we're going to get nimbostratus clouds like we have today as I'm filming this. And you're going to get light to moderate precipitation out of that. But you're not going to get a thunderstorm on a warm front. Okay, how about the cold front? The cold front is on the trailing edge or the back edge of our mid-latitude cyclone. A cold front means cooler air is moving in. It's shown as a blue line with triangles. Thunderstorms are possible, especially in the warmer months, and you might even get supercell thunderstorms, which are the really big, powerful, dangerous thunderstorms. So, the supercell thunderstorms are more likely to occur late spring, early summer. So, if your cold front's moving in and you have a large enough difference in the air density before the front and behind the front, large enough difference in air density that you're going to build a thunderstorm, then you expect to see cumulonimbus clouds. Okay, those are the really tall, towering clouds that signify a thunderstorm is moving in. When I was growing up, we used to nickname them thunderheads. So, bottom line here is that last bullet. Violent weather is possible along your cold fronts, especially in the warmer months, but at least it will move out quickly. Okay, this brings us to tornadoes, which is the last, well, almost last topic for our video lesson. Hurricanes is actually the last topic for the unit and for the semester. Hurricanes is covered in the narrated PowerPoint. I didn't talk about hurricanes in class today, therefore I'm not going to put it on a video lesson. Okay, so tornadoes. I'm going to want you to know when is tornado season, and that's in quotes because it's not a real season like summer or winter. It's simply the time of year when they're most likely to occur. Tornado season, April through June. I'm going to want you to know what was the worst year for tornado outbreaks, and that was 2011. In the narrated PowerPoint, we discuss the terrifying tornado outbreaks that we had in April and May of that year, and we discussed it in class today. Where are we likely to see tornadoes form? They are going to form not with just any thunderstorm, not your everyday afternoon air mass thunderstorm on a hot day in the summer, that's just a thunderstorm, but they're going to form along the supercell thunderstorms that can form along cold fronts. We can also see tornadoes spin out from tropical storms and hurricanes. Dorian, that was last fall, so we were spared the wrath of Dorian here at school, but there were some effects at the coast, and Dorian produced a handful of tornadoes. I'm going to want you to know the difference between tornado watch and tornado warning. A tornado watch is issued when the conditions are favorable for tornado formation. If you have a supercell thunderstorm moving into your area or a tropical storm or hurricane making landfall, they will issue a tornado watch. It means you got to stay awake, pay attention, because a tornado could happen. Now, a tornado warning, they won't issue until one has actually formed and touched down, and it's either been spotted by people on the ground, or even if it forms in a, say, a big field and nobody sees it, we will know it's there because of its hook echo signature on Doppler weather radar. All right, one last quick topic here for our last video lesson for the semester. Okay, winds. Where to stand, not be too close and not be too far away. Okay, so there are probably several pages of winds in your textbook, whatever chapter that is. It's either 17, 18, or 19. But we can't ever cover every chapter in a textbook, ever. And nobody should even try. We have a whole nother class called Atmosphere and Weather. I'm sorry, it's called Weather and Climate. I teach it in the fall, Dr. Edgell teaches it in the spring. All right, so just a snippet here. All we're going to learn about wind for our semester is this. The underlying cause of wind is the unequal heating of Earth's surface. So, as you will see in a narrated PowerPoint, or as we did in class together if you were here, Earth is heated more so at the equator and within the tropics. So basically from 23.5 degrees north latitude to 23.5 degrees south latitude, those people will get the most heat. And then of course at the poles, the Earth is heated much less. So what's the definition of wind? Okay, that second bullet there is a short answer question on your last exam. Wind is the horizontal flow of air from high pressure to low pressure. So air molecules will always move from high pressure to low pressure. And when we feel that, we call that wind. Okay, so that is it for our video lesson for the atmosphere and weather unit.